Hi, and welcome to your Introduction of Organic Chemistry. We're going to start with a very important organic molecule, caffeine. If you see these little black spheres that are in this molecule, those are carbon atoms. And carbon is the basis of all organic molecules. And so what if we didn't have carbon? Like, why do we even need these organic compounds? Well, the answer is they make up your entire body. So all of these chemical reactions that happen in your body, they happen because of organic molecules or molecules containing carbon. Remember that carbon is a nonmetal, so it makes covalent bonds. Every carbon will make 4 bonds because it has 4 valence electrons. And these organic molecules are usually going to be very large with very high molar masses. Hydrocarbons are going to be the simplest kind of organic molecule you can have. All they have are carbon and hydrogen. So propane in your barbecue grill or methane that heats your home. And the simplest kinds, all they can do is combust. So our prefixes meth, eth, prop, and bute for 1, 2, 3, and 4. After that, you'll notice they're very much like covalent prefixes minus the a. So pent for 5 now becomes penta. So to remember those first 4, remember monkeys eat purple bananas, and that will help you keep them in order. So of our hydrocarbons, our basic types of organic molecules, there are 3 kinds. Alkanes have only single bonds, so between this carbon you'll see single bonds. And we name them by the prefix for the number of carbons, so 1, 2 is eth, ane because there's only single bonds. To figure out the formula of our alkane, we take our prefix, so eth would be 2, and that's going to become the subscript for our carbon. To figure out the subscript for our hydrogen, or how many hydrogen atoms we have, we take the number of carbons times 2 plus 2. So what if there were multiple bonds between the carbons? That actually is going to allow our molecules to go through some more interesting chemistry and some different reactions, which are going to be the focus of our future videos. Alkenes contain a double bond. So between these carbons, you'll see 2 bonds. So again, 2 carbons is eth, ene for the double bond. I call this ethene. Again, there's going to be a generic formula. You'll notice that it's very much like the alkane formula, except the plus 2 is gone, because when I formed this second bond between the carbons, I lost 2 spots for hydrogen. A triple bond between the carbons is called an alkyne, and that alkynes, when they formed that triple bond, lost another 2 spots for hydrogens. So again, in the generic formula, you're going to see a minus 2 because of the loss of 2 hydrogens to form that triple bond. 2 carbons is eth, ine for my suffix, so ethine. The common name for this is acetylene. So acetylene torches are used a lot in welding. So what do these multiple bonds do? They actually will make these molecules a lot more friendly for your body. So you've heard of saturated fats or unsaturated fats. We also say saturated and unsaturated compounds. Saturated means that there's only single bonds. So again, all that these can do is burn. So literally catch fire, which means your body can't do a lot with them. Unsaturated compounds have double and triple bonds, which gives them more options for reactions that they can go through. So that's why unsaturated fats are a lot better for your body than saturated fats are. Well, what if all we had were these basic hydrocarbons, the alkanes, the alkenes, the alkynes? We actually don't have a lot of chemistry that goes along with them. So what we do is we add functional groups. So if there were no functional groups, if there was nothing interesting on these chains of carbon and hydrogen, what would happen? The answer is nothing. These molecules wouldn't be able to react. You wouldn't get things like the proteins and the carbohydrates and the lipids that your body needs in order to function. So that's why we call them functional groups. They allow our molecules to function. So you have your hydrocarbon stem, so 2 carbons, like we named them with eth, and then you'll have your functional group put on the end. This one happens to be called an alcohol group. So this is ethanol, which is the most common form of alcohol, or in other words, the drinkable kind of alcohol. There are 5 functional groups that we're going to be concerned with right now. We will add more later. The first is an alcohol. In biology, sometimes they call them hydroxyl groups. So this R is going to stand for the stem or the rest of my molecule. So in other words, if I had 2 carbons or 3 carbons, the eth or the prop, that would be the chain or the rest of my molecule. This OH is going to be as part of my formula, and that OH can actually be anywhere. So down here, this OH is currently in the middle, but it could have been on either end of the molecule also. When I name these, a nol is going to be my prefix. So this alcohol group is on the second carbon of 3. So prop is my stem, a nol is my suffix, and 2 is where that alcohol group is, 2-propanol. When I write out its formula, I'll put the C with the OH behind it. Anything written behind a carbon belongs to that carbon. Aldehyde groups have to be on the end because there are 4 bonds that carbons make. 2 of them involve a double bond with an oxygen. 1 of them is a single bond with a hydrogen. So when I write their formula, CHO is going to be on the end of that formula. Anal is going to be my suffix. So here I have my aldehyde group. It only involves 1 carbon, so meth-anal, commonly known as formaldehyde. Carboxylic acids are sometimes called carboxyls in biology. They also have 3 of their carbon's 4 bonds tied up in the functional group, so they have to be on the end. 2 bonds make the double bond with the oxygen. 1 bond makes a single bond with the oxygen in the OH group. They have to be at the end, so the other side is going to be the rest of the molecule. So when you write the formula, COOH will go on the end. Anoic acid is your suffix. So for this guy, I've got 2 carbons. This is my carboxylic acid group. So eth for 2 carbons, anoic acid for my carboxylic acid group. This is commonly known as acetic acid or vinegar. Ketones go in the middle. So they have to be in the middle. So you'll have part of the molecule going off to the left, part of the molecule going off to the right. So CO is how you show that in the formula. Unknown is how you put it on the end. So this has 1, 2, you assume there's a carbon when a bunch of lines meet. 3, so prop, unknown, also known as acetone or nail polish remover. Halides, think halogens. So anything from group 17, fluorine, chlorine, bromine, or iodine. An X is what you use when you don't know which one you have. Halo is the prefix that you put on the end when you don't know which one of the elements you have. When you do know, you replace halo or the X with the symbol or the name. So bromine becomes bromo, you have chloro, iodo, and fluoro. So for example, I have 2 carbons. This is bromoethane. 3 carbons would be chloropropane. When I name them, the people who got to come up with the naming rules are the International Union of Pure and Applied Chemistry. And they say that you start with your longest chain. So in other words, you start at the end, count how many carbons you have, and that's your prefix. The functional group is going to be the suffix at the end of the name. If you have chains, those are prefixes that go at the beginning. Our halogens count as a prefix or count as a side chain, and so do our groups of carbons. We're going to start out with the simplest one. 1 carbon is a methyl group. You show where it is by a number at the front of the name. So we've done this before. Our alcohol group is on the 2nd carbon. We number them so that you get the smallest number. So I'm going to number this from the left because that gives me 2 bromo. Remember, this bromine belongs to the carbon in front of it. If I numbered from the right, it would be the 3rd carbon. So I want the lowest numbers. Side chains can be written in parentheses. So this parenthesis tells me that it's not part of my full chain. So 1, 2, 3, 4, 5 carbons in my chain would be pent. The 2nd carbon from the end has the methyl group, so that would be 2-methyl pentane. If there's more than 1 side chain, then you show that with di or tri. So 2 chlorines would be 1,3-dichloropropane because they're on the 1st and the 3rd carbon. When you draw them, start with your prefixes, write out your number of carbons, place your functional group at the end unless there's a number telling you where it should be, put your side chains on your correct carbons, so your methyls and your halides, and then put hydrogens on every carbon so everybody gets 4. Be sure to complete your examples, fill in your questions, main ideas for class, and write your summary for your Cornell notes, and I will see you in class.